So in this video, we're going to be addressing a couple of new terms and concepts. So today we're going to talk about spanning vectors, and the new terms for today would be independent versus dependent vectors, coplanar, spanning vectors, and linear combinations.
So in this slide, we have two vectors, the blue one and the red one. Now the blue one is going south with a magnitude of 1 because the length is 1. We call this a unit vector because it has a value of 1, the magnitude. The blue one is parallel to the red one. So these two vectors, the blue and the red, are collinear. Collinear is a word that tells you that the two vectors are parallel to each other. Now, however, the blue one has a different magnitude of 2 and it's going north. So we have two vectors in different directions. So when two vectors are collinear or parallel, they are called dependent vectors. And the reason why it's dependent is because we can express the two vectors in an expression where one is dependent on the other. So for example, let's look at the blue and compare it to the red. We can see right here that the blue is double the size of the red. So what that means is we can write the blue in terms of the red vector. So if you're to choose one of these multiple choice questions, which one do you think is correct? Is the blue the same thing as the red? Well, it's not true because the magnitudes are different, the sizes are different. So the first statement is not true, but the second statement, well, the blue is twice the size of the vector. Well, it is true that the blue is the same, is double the size of the red vector, but however, they are going in opposite directions. If I were to draw a vector expressing this, the red has to be in the same direction as the blue, but they are in different directions. So the last statement, blue, is twice the red vector. Yes, the size is twice, but if you notice the negative, this means in order for the red or the blue to be in the same direction, one of the vectors has to be negative. And if you can express a vector in terms of each other, those two vectors are dependent on each other. They are collinear. So let's do some operations on these vectors. So let's just say on my left-hand side, I'm going to take the red vector and I'm going to put a 2u. So what 2u means is, as you can see here, see this vector over here? That means it has doubled the red. That's why it's going in the same direction, but it's double the size. If I change this vector, the blue, let's call it the blue, the v. Let's say that I change it to a 2v. What happens? So you notice here, this dark gray vector, it has doubled the length of the blue. So what that means is, based on previous sections of this unit, you can do something called scalar multiply. So scalar means to multiply a number by the vector. And when you multiply a number with the vector, the size changes or the direction changes. For example, if I took the blue vector and multiplied by, for example, let's just say negative 3v, what's happening is you're going to have, so the blue vector is being tripled. So if I make this thing smaller, you'll notice that the vector here right now goes to 6, but notice it's a negative. That means instead of going north, your new vector that you multiply by negative 3 is going south. So let's just start adding these vectors. So the u is the red, the v is the blue. So let's take these two vectors and add them. What happens? So let's look at the right screen. Notice how you have this vector over here, all right? So look at the vector here, this gray one here that we can't see that clearly, but notice that this vector is also collinear, parallel to the blue and the red. Let's try another operation. Let's go to the left and let's do u minus v. Oh, so now if you notice here, we have this gray vector. It's different magnitudes, but notice how it's this gray vector, the resultant vector is also parallel or collinear or dependent. So over here, I'm just going to play around with this, 2u plus 3v. 3v, what happens? Oh, we have another vector that is also collinear or dependent. So the point of this section of the video is, no matter what I do to these vectors, so let's just say I did a negative u and plus 3v. All right, no matter what happens, basically what's happening is I create a brand new vector which is also collinear. It is either going north or south. So the idea of this is, if you take two vectors, two parallel vectors or dependent vectors or collinear vectors, and if you do, either you multiply, scalar multiply, add, subtract these two dependent vectors, you're going to get a vector that is also collinear. meaning going either north or south. So no matter what you do, you always get a vector that's always either going north or south. In this particular example, there's absolutely no way you can make a vector that's going east or west or northeast. So here we have two vectors, the red and the blue, and here are their components to the left. So 2, 3 means you're going to go 2 to the right and 3 up. This one here, -1, 2 means you're going to go from the origin to 1 to the left and 2 up. That's how we get those two vectors. So these two vectors are clearly not parallel to each other. What that means is you cannot write, for example, the blue is equals to, for example, half the red. There's absolutely no way you can express these vectors in terms of each other because they're not parallel or collinear or dependent. Now, being independent, so we call these two vectors independent. So let's just say if I take these two vectors and add them, let's see what happens. Oh, we've created a brand new vector, this gray one, which has nothing to do or not parallel to any of these two vectors. Or let's just say I took v minus u, I subtract these two vectors, I create a brand new vector which is going in a different direction compared to the other red and the blue. Let's just say I doubled the red one and then I subtracted, for example, 3v, the blue one. Where did it go? Oh, it somehow lands on the x-axis over here. So the idea I'm trying to show is that no matter I'm doing operations, we call this linear combinations. Linear combinations means if I take a vector and I multiply it and I subtract it, I do another operation, let's just say minus u, I end up getting a vector. So I'm doing linear combinations. I'm combining two lines or two vectors. I'm doing something to them, either adding, subtracting, or scalar multiplying, making them longer or shorter, and I create a brand new vector. And if you notice, these vectors that I'm creating are not linear, or sorry, they're not collinear or parallel to these vectors. What that means is I can create vectors from the red and the blue and create another vector which goes in a different direction. And what that means is these red and blue, these are vectors, they are independent of each other, and they also span. So the new word for today is span. Spanning means to create a new vector which is going in a different direction compared with your two given vectors. Meaning it can go, you can create a vector that goes in any direction that you want if you do something to these two vectors, linear combinations with these two vectors.
So let's now do a couple examples to determine whether vectors span or not span. So let's have a look at the first example. So for example is vector u, 2, 3, and 4, 6. And you can see that the vector v, seems to be doubled u, and you can check it out by doing the following. Let's sub in 2 and 3 into the unit vector part, and then, the vector part, and we end up getting distributive property gives you 4 and 6. So what that means is v and equals to 2u, meaning they are dependent, they are collinear, they're parallel. What that means is if you're to do linear combination on this, you're not going to be going in a different direction. You're always going to be going in the same direction or parallel to 2 and 3 or 4 and 6. So in these cases, these do not span because they are dependent. Now the next one here, 1, 1 and 2, negative 2. And we know that b is not doubled too because b, if I do this statement is not true because the signs are different. And even if you try to test it out, if you take vector A and doubled it, you end up getting 2, 2, which is not the same thing as this. So what that means is these two vectors are not parallel to each other. They are independent, and therefore they will span, meaning if you add or subtract them or do some linear combinations on these two, you're going to create another vector that is neither parallel or collinear to these two vectors. In the last example here, you have 4 and 6 and 6 and 9. You might think, there's no relationship between the two. However, if you want to find that common constant multiple, meaning if you want to figure out what k is, that k factor, you can actually take the 6 and divide it by the 4, which gives you 3 over 2, and you want to check whether the y part actually works. So let's take 9 over 6 and 3 over 2. So what that means is to get from here to here, you're going to multiply by 3 over 2, or you can say that the n vector is 3 over 2 times the m vector, or you want to be a little more other way around, different perspective, you can say that the m vector is shorter than the n vector by a certain amount, that fraction. So in this case, we can express these two vectors in terms of each other. Therefore, these two vectors are dependent meaning they are parallel or collinear, and therefore they do not span. So in this example, we have two vectors that are already given, and you can see that these two vectors are not multiples of each other, therefore they are independent. And basically what I can do is I can do something, scalar multiply by something with the u vector, and maybe add or subtract to the v vector in order to create another vector that is not collinear to these. So 1 and 3, as you can see, they're not multiples of each other. They're not really related to each other. All right, so the question right now is, what do I have to do to u and v in order to get this brand new vector? In other words, let's actually sub in what we know for u, which is 1, 1 plus b 2, 3 is equals to 1 and 3. And our goal is to solve for a and b. That's the goal. So let's actually do distributive property here. In this case, let's just multiply everything by a. So everything is still in component form, 3b. And what we're going to do is we're going to address just the x of component. So the x and the x. So you're going to say a plus 2b is equals to 1. And then we have the y component, which we'll use blue. We know that a plus 3b is equals to 3. And now we have two equations, two variables. Let's solve for a and b. So I'm just going to put the blue one underneath here. I'm going to do elimination. The a's are nicely set up. So I'm going to subtract the bottom minus the top. I get b is equals to 2. I'm going to sub back b for 2 into, let's just say, the top equation to solve for a. And then I end up getting a is equals to negative 3. What that means is that in order for me to get the w vector, I'm going to have to do something to the u vector and the v vector. And what is that? Well, what's a? A is going to be negative 3, and 2 is going to be the b. So what that means is I have to take the u vector, triple it, go in the opposite direction, and then add it physically to double the length of the v vector in order for me to get the w. So over here, our final conclusion is these are my linear combinations on u and v in order to get the w.